The universe is expanding. That much we know. But here's the uncomfortable part. We don't know where it's going or what's driving it. Galaxies aren't just drifting apart. They're racing away from each other faster and faster, like cosmic dots on an inflating balloon. Something unseen is pulling the fabric of space outward, stretching it with growing urgency. But what is it expanding into? Will it slow down, reverse, tear itself apart?
This is a question about reality, about time, space, and what it means to exist in a universe that's quietly evolving and possibly destined for a very strange end. Let's explore the clues we've gathered so far, from the strange fingerprints left in the cosmic microwave background to competing visions of how it all might end.
Revisiting Hubble's discovery, expanding horizons.
In the early 20th century, astronomy was still focused mostly on our own galaxy. Many scientists believed it was the entire universe, that everything that existed was part of this one great island of stars. Some distant fuzzy patches in the sky, called nebulae, were thought to be gas clouds inside the Milky Way. The true scale of the cosmos was still hidden, but all of that changed when a man named Edwin Hubble turned his telescope toward the Andromeda Nebula.
Working at Mount Wilson Observatory in California, Hubble used one of the most powerful telescopes of his time, the 100-inch Hooker telescope. In the early 1920s, he began carefully studying variable stars within Andromeda. These stars, known as Cepheid variables, have a special trait. Their brightness changes in a predictable pattern, and the time it takes them to go from bright to dim can be used to figure out how far away they are. This gave astronomers a kind of cosmic measuring stick.
When Hubble calculated the distance to these stars, he made a discovery that would shake the foundations of astronomy. Andromeda was far too distant to be part of the Milky Way. It wasn't a nebula inside our galaxy, it was a galaxy of its own, a whole other system of stars, hundreds of thousands of light-years across, separated from us by over 2 million light-years of space. Hubble had proven that the universe was far larger than anyone had imagined. Once it was clear that other galaxies existed, astronomers started to ask another question. How are these galaxies moving? Are they drifting toward us or away from us? Are we in the center of the universe, or just one point among many? To answer this, scientists turned to a tool called spectroscopy. When light from a distant galaxy passes through a prism or a diffraction grating, it spreads into a spectrum, much like sunlight through a raindrop creates a rainbow. Within that spectrum are dark lines caused by elements in the galaxy's stars absorbing certain wavelengths of light. These lines serve as fingerprints for atoms like hydrogen, helium, and others. But if a galaxy is moving, the position of those lines can shift. If it's moving toward us, the light is squeezed, shifted toward the blue end of the spectrum. If it's moving away, the light is stretched out, shifted toward the red. This effect is known as the Doppler shift. When Hubble and his colleague Milton Humason examined the light from distant galaxies, they noticed something remarkable. Almost all of the galaxies were redshifted. They weren't coming toward us, they were moving away. And not only that, the farther away a galaxy was, the faster it seemed to be receding. The pattern Hubble found was clear and simple. Distance and speed were linked. This relationship is now called Hubble's law. It meant that the universe wasn't static, it was expanding. Space itself was stretching, and the galaxies were being carried along with it, like raisins spreading apart in a rising loaf of bread. At the time, the idea of an expanding universe was hard to accept. Even Albert Einstein had originally introduced a cosmological constant into his equations to keep the universe from expanding or collapsing. He thought the universe should be balanced and still, but Hubble's discovery showed that wasn't the case. When Einstein learned about the evidence, he reportedly called the cosmological constant the biggest blunder of his life. The idea of an expanding universe was radical. It meant that if the galaxies were all moving away from each other now, then in the past, they must have been closer together. Keep going back far enough, and you'd reach a time when everything was in one place. This was the beginning of what would later be called the Big Bang Theory.
The redshift became one of the most powerful tools in cosmology. It allowed astronomers to measure how far away objects were and how fast the universe was growing. Over time, more precise measurements were made using better telescopes and more detailed spectroscopic data. The value of the Hubble constant, the rate at which the universe expands, became a central question in astronomy.
Today, we can look back at galaxies so distant that their light has taken over 13 billion years to reach us. The farther we look, the more redshifted their light becomes, stretched by the expansion of space itself. In fact, some galaxies are now moving away from us faster than the speed of light. Not because they're breaking the rules of physics, but because space is expanding so rapidly at those vast distances.
This idea is a direct result of Hubble's work. His findings not only changed how we see the universe, but also how we understand time, space, and even the origin of everything.
The Hubble constant conundrum, tension unresolved.
The Hubble constant tells us how fast the universe is expanding.
If you know this number, you can estimate the size of the universe, its age, and how long ago the Big Bang happened. For decades, scientists worked to measure it more and more accurately. But something unexpected happened. As the tools became better, the numbers didn't start agreeing, they started to drift apart.
The idea of the Hubble constant goes all the way back to Hubble in the 1920s. The relationship between the speeds and estimated distances of galaxies became the foundation for the Hubble constant, which describes the rate of expansion in units of kilometers per second per megaparsec. That means for every megaparsec of distance, a little over 3 million light years, galaxies are moving away at a certain number of kilometers per second.
At first, Hubble's measurements weren't very accurate. He overestimated distances, and the value he found was far too high. But that wasn't surprising. The tools he used were primitive by today's standards. Over time, as telescopes improved and scientists learned more about the stars and galaxies they were measuring, the value was refined. For many years, the goal was simply to get everyone to agree on one number, and eventually they did, or so it seemed.
Things changed when different types of measurements began to give conflicting results. One of the most trusted methods involves what we see in the early universe. The Planck satellite, which mapped the cosmic microwave background (CMB) in great detail, gave us one of the most precise measurements ever. It calculated the Hubble constant based on conditions just 380,000 years after the Big Bang, using models of how the universe evolved.
From then until now, it predicted a value of about 67.4 kilometers per megaparsec. But then another team measured the expansion using much closer objects, type Ia supernovae in nearby galaxies. These are standard candles, which allow scientists to calculate distances directly. They compared those distances with the galaxy's redshifts to get the Hubble constant in the present day. Their result came out to about 73 kilometers per megaparsec.
That's a noticeable difference, and it's not just a matter of small errors. The numbers are far enough apart that they can't both be correct, unless something important is missing from our understanding of the universe. This conflict has become known as the Hubble tension, and it hasn't gone away. In fact, the more data scientists gather, the more solid both results appear to be. Measurements from the early universe and measurements from the late universe continue to give different answers.
The question now is why the two methods don't agree. One possible answer is that one or both are missing something. Maybe the models we use to go from the early universe to the present aren't quite right. Or maybe something strange happened along the way, something the models don't include. Some scientists have even suggested that dark energy might not be constant, but instead changes over time. If that's true, it would affect how the universe has expanded. Others think the problem might be in the measurements themselves. Supernova data depends on how well we understand these explosions. If their brightness changes slightly over time, or if they behave differently in the early universe than they do now, that would throw off the results. It's also possible that the galaxies being used are not typical, or that something in the dust between us and them is interfering with the light we see. Meanwhile, the early universe measurements depend heavily on a model called lambda cold dark matter, or lambda CDM. This model has done a great job of explaining many things like the structure of the universe and the behavior of galaxies, but it also relies on certain assumptions, including that dark energy is constant and that dark matter behaves in predictable ways. If any of those assumptions are wrong, then the value of the Hubble constant calculated from the early universe might be off. In response, scientists have looked for other ways to measure the expansion rate. One promising method involves gravitational lensing. When a distant object like a quasar is lensed by a closer galaxy, the light can take multiple paths to reach us, arriving at slightly different times. By studying the time delay between these light paths and combining that with redshift data, researchers can calculate distances and the Hubble constant independently. These lensing-based values tend to agree more with the supernova measurements than with the early universe predictions. Gravitational waves may also help resolve the tension. When a neutron-star merger is observed in both light and gravitational waves, scientists can calculate how far away it is and compare that to redshift. These standard sirens are still rare, but over time they may provide a third, unbiased way to measure the expansion rate. The tension has sparked deep discussions across cosmology and physics. Some researchers see it as a crack in the foundation of the standard model of cosmology. Others are more cautious, saying we need even better data before jumping to conclusions. But one thing is clear: this is not a small problem. It strikes at the heart of how we understand the universe. The search for answers has also led to new missions and telescopes being designed with this question in mind. The Nancy Grace Roman Space Telescope, set to launch in the coming years, will provide an even more detailed map of the sky and help refine both supernova and lensing measurements. The European Space Agency's Euclid mission will look closely at dark energy and structure in the universe. These missions aim to get to the bottom of the Hubble tension and find out whether it's pointing to a deeper truth about the cosmos.
Dark energy, the engine behind acceleration.
In the late 1990s, astronomers were measuring the speed at which distant galaxies were moving away from us. The goal was to find out if the universe's expansion was slowing down over time, as most people expected. The idea made sense. Gravity pulls things together, so as the universe expands, its growth should gradually slow. But what they discovered was completely unexpected.
Instead of slowing down, the expansion was speeding up. Galaxies weren't just drifting farther apart. They were doing it faster and faster. Something was pushing the universe outward. That something was given a name: dark energy.
Dark energy is one of the biggest mysteries in science. It makes up about 70% of everything in the universe, but we don't know what it is. We can't see it, touch it, or detect it directly. All we know is that it's there because of what it does. Its presence is felt through its effects on space itself.
It stretches the universe, making distant galaxies move away from each other at an increasing pace. To understand what dark energy might be, scientists started looking at how it behaves. The first clue came from those distant supernovae. Using them, scientists could figure out how fast the universe was expanding at different times in the past.
When they did this, they saw that the expansion was slower, billions of years ago than it is now. That meant something had changed. Something started to overpower gravity. That something was dark energy. But what exactly is it?
One idea is that dark energy is a property of empty space. This concept goes all the way back to Albert Einstein's cosmological constant. He did it to keep the universe static. He thought the universe neither expanded nor collapsed, and the constant was used to balance out gravity.
When the universe's expansion was discovered, he called it his biggest blunder. But decades later, it came back into the picture because it could explain dark energy. If space has energy built into it, then as the universe grows, more space means more energy. That energy doesn't get diluted like matter does. Instead, it stays constant per unit of space.
So, as space expands, the overall energy increases. That energy acts like a kind of anti-gravity, pushing everything apart. This is what the cosmological constant explains. It's a simple idea and fits the data fairly well.
Still, not everyone is convinced this is the full story. Some scientists think dark energy might not be constant at all. It could be changing over time, or it might behave differently in different parts of the universe. These ideas lead to something called quintessence. That's a name for a type of dark energy that can vary in strength.
Unlike the cosmological constant, quintessence would act like a dynamic field, something that fills space and evolves as the universe ages. There are many forms quintessence might take. Some versions weaken over time, others grow stronger. A few might even reverse direction at some point, slowing expansion instead of speeding it up. These different possibilities all have different consequences for the future of the universe. If the force continues to push space apart at an ever-increasing rate, galaxies will get farther and farther away. Eventually, they'll move so fast that their light will never reach us again. The universe will grow colder and darker as stars burn out and black holes slowly evaporate. This is called the Big Freeze. It's one possible ending where the universe just keeps expanding forever, becoming emptier and lonelier with time. Another scenario, though less likely based on current data, is the Big Rip. In this case, dark energy grows stronger over time. It doesn't just push galaxies apart, it starts tearing galaxies themselves apart. Then it rips stars from planets, atoms from molecules, and eventually even the particles that make up atoms. This would be the most violent end imaginable, where everything is torn to pieces in the final moments. Then there's the Big Crunch, which would happen if dark energy eventually weakens or turns negative and gravity takes over.
Again, in this case, the universe could stop expanding and start collapsing. Everything would fall inward until the universe ends in a kind of reverse Big Bang. But current observations don't support this idea, at least for now. To test these theories, scientists need to study dark energy more closely. That means mapping the universe in more detail, measuring how galaxies cluster, and seeing how expansion has changed over time. The more data we get, the better we can understand how dark energy behaves.
One important tool for this is baryon acoustic oscillations, or BAO. These are ripples in the distribution of galaxies caused by sound waves that moved through the early universe. By measuring the size of these ripples at different distances, scientists can see how the universe expanded over time. These measurements give clues about how strong dark energy was in the past. It's strange to think that most of the universe is made of something we don't understand at all. Matter, the stuff we see, touch, and measure, makes up less than 5% of everything. Dark matter, which we also haven't fully identified, makes up another 25%. But dark energy is by far the largest part and the least understood.
Some scientists even wonder whether dark energy is pointing to a flaw in our basic understanding of physics. Maybe general relativity is incomplete. Perhaps gravity works differently on very large scales. If that's the case, then what we're calling dark energy might be the result of a deeper law we haven't discovered yet.
Unveiling cosmic topologies beyond simple geometries. When most people think of the shape of the universe, they imagine something simple, a vast, empty space that either stretches infinitely in all directions or curves around like a giant sphere. In popular discussions, the universe's geometry is often described as either flat, like a sheet of paper, or curved, like the surface of a ball. These ideas are based on the most common models of cosmology, where the universe is thought to behave according to either Euclidean or spherical geometry.
However, in recent years, scientists have begun to explore more complex possibilities, ideas that challenge the simple assumption that the universe is either flat or curved in a straightforward manner. Could the universe have a more exotic structure? Could it have strange geometries that twist and fold in ways that are nearly impossible for us to comprehend?
The search for the true shape of the universe is leading scientists into the realm of new, less familiar topological models. The geometry of the universe is closely tied to the fabric of space-time, the four-dimensional stage on which everything happens. According to general relativity, the shape of this stage isn't fixed. It can bend and warp, depending on the distribution of matter and energy. This warping is what causes the effects we observe, like gravity. The overall geometry of the universe influences how galaxies move, how light travels across vast distances, and even how the universe will evolve in the future.
One of the simplest geometries proposed for the universe is the idea of a flat universe, in which space extends infinitely in all directions with no curvature whatsoever. This is what we find when we look at the most detailed observations of the CMB. According to current measurements, the universe seems to be very close to flat. This means that on large scales, space behaves as though it follows the rules of ordinary geometry, with parallel lines never meeting, angles adding up to 180 degrees.
However, the flat model only tells part of the story. It assumes that the universe is uniform and unchanging on a large scale, which is generally true for the most part. But some scientists have argued that this simple picture doesn't capture the full complexity of the universe's structure. They believe that the cosmos may have a more intricate and subtle shape.
In this view, the universe could have a higher dimensional structure that's difficult to visualize. Just like a two-dimensional surface can be flat, cylindrical, or spherical, the universe could have a multi-dimensional shape that's impossible to describe in our everyday experience. Imagine, for a moment, a surface with a strange twist, a kind of donut shape. If you were to travel far enough in a straight line in this world, you might eventually return to where you started, but through an unexpected route.
This idea is based on the concept of a closed universe, where space itself is finite but has no boundaries. It's not like a box with walls, but more like a loop, where traveling far enough in one direction would bring you back to your starting point. Such a closed, looping universe would not only have a surprising shape, but it would also have far-reaching consequences for how we think about space and time.
These topologies are often described in mathematical terms, but imagining them is a different matter entirely. Some researchers have proposed models where the universe has a kind of multi-connected structure. In this type of model, space might contain mysterious holes, or wormholes that connect distant regions. The idea is that space itself could be folded in such a way that traveling through one of these wormholes would instantly take you across vast distances.
In some versions of this theory, entire galaxies could be linked by these hidden bridges, and the light we see from distant parts of the universe might not be traveling along the path we think it is. Instead, it could be bending and twisting through higher dimensional connections, creating what we call non-trivial topologies. In one of the most radical ideas, some scientists have suggested that our universe could be part of a larger structure, a higher dimensional multiverse. In this view, our universe would be just one of many, each with its own set of physical laws and properties. These universes could be connected through higher dimensional spaces, with our own universe possibly forming a kind of bubble in this greater multiversal structure. These bubbles might interact with each other, and some researchers have even speculated that the collision of two such universes could have created the Big Bang itself.
Some topological models suggest that the universe could have a repeating or periodic structure. Imagine that, on the larger scales, space might contain regions that mirror each other, almost like a cosmic version of wallpaper patterns. This could mean that the universe is structured in a way that repeats itself, with each copy of the universe connected to the others by an underlying mathematical rule. This kind of model could explain some of the observed patterns in the universe's structure, including the arrangement of galaxies and galaxy clusters.
Another intriguing possibility comes from the idea of a universe that is not only multidimensional but also fractal in nature. Fractals are patterns that repeat themselves on different scales, like the branches of a tree or the coastline of a jagged mountain. If the universe were fractal, this could mean that the structures we see on large scales, like clusters of galaxies, might have similar patterns on much smaller scales, all the way down to the tiniest subatomic particles. In this case, the universe would be made of repeating self-similar structures, and this could have profound implications for everything from the distribution of galaxies to the way that space-time itself is structured.
Much of the work being done in cosmology today focuses on trying to figure out which of these models best matches what we observe. The complexity of these topological structures means they are hard to test with current technology, but researchers are not giving up, and new tools, better measurements, and more powerful computer simulations are helping to build a clearer picture of the universe's shape.
Gravity's role in a multifaceted cosmos. Gravity keeps our feet firmly planted on the ground, pulls objects toward the Earth, and shapes everything from the paths of falling apples to the orbits of planets. While we typically think of gravity through the lens of Newton's laws or Einstein's general relativity, recent discoveries suggest that gravity may be far more complex, especially when applied to the enormous scales of the universe.
According to relativity, gravity isn't just a force that pulls objects together, but rather the result of the bending of space-time caused by mass and energy. Massive objects like the Earth or the Sun warp the space around them, and this warping is what we experience as gravity. The more massive an object, the greater the curvature of space-time it creates.
While general relativity has been confirmed through numerous experiments and observations, its application to large-scale cosmology on the level of galaxies and the entire universe reveals some strange puzzles. For instance, the universe's accelerating expansion challenges traditional expectations about gravity's role in the cosmos. Why does gravity seem to behave differently on cosmological scales?
Some possible explanations come from theories that add modifications to general relativity. One such theory is called modified Newtonian dynamics, or MAMDA, which was first proposed by physicist Mordechai Milgram in the 19th. Monand suggests that gravity behaves differently at very low accelerations, such as those found in the outer regions of galaxies. According to this theory, the gravitational force doesn't follow the simple inverse square law we are familiar with at large distances. Instead, the force weakens more slowly than expected, allowing galaxies to hold onto their stars and gas clouds more tightly than traditional Newtonian gravity would predict.
Mond has had some success in explaining the behavior of galaxies, particularly their rotation curves, the way stars move around the center of the galaxy, but it hasn't been universally accepted. One of the major challenges of Mond is that it doesn't explain everything, particularly when it comes to the behavior of galaxy clusters and the cosmic scale of the universe.
Another alternative to general relativity is the idea of a fifth force, or a modification of gravity at larger scales. In this scenario, gravity might not be the only force affecting the universe's evolution. There could be a new force at work, one that influences cosmic expansion and alters our understanding of gravity's role in the cosmos. Some scientists have suggested that such a fifth force could be tied to dark energy. In this view, gravity is still responsible for the formation of galaxies and stars, but there is an additional force that comes into play at larger scales, one that acts to push the universe apart rather than pull objects together.
In some models, gravity could weaken or strengthen depending on the age of the universe or the distribution of matter. If gravity behaves differently in different parts of the universe, this could have profound effects on the evolution of galaxies and the expansion of the cosmos. For instance, if gravity were weaker in the past, galaxies might have formed more slowly, or stars might have burned out at different rates. The exact nature of this time-varying gravity is still up for debate, but it has the potential to radically change our understanding of the universe's history and future.
Then there is the concept of quantum gravity, which attempts to combine the principles of quantum mechanics with general relativity. At the smallest scales of reality, such as those involving elementary particles, quantum mechanics governs the behavior of matter and energy. But when we look at the large-scale structure of the universe, the laws of general relativity take over.
Quantum gravity seeks to explain how gravity works at these tiny scales, where the effects of both quantum mechanics and gravity are felt simultaneously. In this realm, the force of gravity might not be smooth and continuous, but instead might exhibit quantum fluctuations, tiny, unpredictable changes in the fabric of space-time. These fluctuations could have important implications for our understanding of the early universe, where both gravity and quantum effects would have played a major role in shaping the cosmos.
One of the most fascinating ideas in quantum gravity is the concept of loop quantum gravity, which suggests that space-time itself is made up of tiny, discrete units, much like atoms make up matter. In this theory, gravity is not the smooth, continuous force described by general relativity, but instead is quantized, existing in small, indivisible chunks. This could lead to a completely new way of understanding the structure of the universe, opening up new possibilities for how the cosmos might have evolved and how it could continue to expand.
Another area of study is the connection between gravity and dark matter. Dark matter interacts with normal matter through gravity, but it does not emit, absorb, or reflect light, making it incredibly difficult to detect. Its presence is inferred from its gravitational effects on galaxies and galaxy clusters.
While scientists have had success modeling dark matter using traditional gravity, it's still unclear exactly what dark matter is. Some theories suggest that dark matter could be made up of particles that interact with gravity in strange ways, possibly involving modifications to our understanding of gravity itself.
The relationship between gravity and dark matter is also central to the behavior of galaxy clusters
These massive groups of galaxies are held together by gravity, and their motion can tell scientists a great deal about the amount of mass present in the universe. The strange way galaxies move in clusters suggests that there is more mass than we can account for with ordinary matter.
Some researchers have proposed that this extra mass could be a manifestation of modified gravity rather than an unknown substance like dark matter. If gravity behaves differently in galaxy clusters, it could help explain many of the anomalies that have puzzled scientists for decades.
All of these alternative theories point to one fundamental truth: gravity, while an essential part of the cosmic story, is far from fully understood. As we continue to refine our understanding of gravity, we may unlock new insights into the forces that govern the universe's expansion and evolution, and perhaps discover a deeper connection between the forces of nature.
The realm beyond the observable, our cosmic horizon in space. There is a boundary that separates what we can observe from what lies beyond our reach. This boundary, known as the cosmic horizon, marks the farthest distance from which light or any other form of information can travel to us since the beginning of the universe. It's not a physical wall, but rather a limit to how much of the universe we can see, measure, and study. Beyond this cosmic horizon lies a realm that remains completely out of view, no matter how advanced our telescopes or technologies become.
The further away an object is, the faster it moves away from us. A relationship that is described by Hubble's law. As the universe expands, the space between galaxies stretches, carrying light along with it. This stretching of space means that light emitted from objects beyond a certain distance will never be able to reach us, because the space between us and those objects is expanding too rapidly. At some point, the distance is so great that the expansion of space is faster than the speed of light, meaning the light from those distant objects will never have the chance to catch up with us. This creates a limit to our observation. What we can see and study is limited by how far light has had time to travel since the Big Bang. The universe is roughly 13.8 billion years old, and that means that light emitted from objects farther than 46 billion light-years away will never reach us, not even in the far future. This region beyond our observational reach is what we refer to as the unobservable universe. But what does it mean to have a universe that stretches far beyond our line of sight? To imagine this concept fully, it's helpful to think about the observable universe as a bubble. Inside this bubble, we can see and study everything from the closest planets and stars to the farthest galaxies and cosmic radiation. However, beyond this bubble lies a vast expanse that remains hidden. These regions are, in a sense, beyond time for us.
One important aspect of the cosmic horizon is that it is not fixed in place. It evolves over time. As the universe continues to expand, the light we observe today from distant galaxies was emitted millions, even billions of years ago. As the universe expands, the galaxies that were once within our observational reach are now moving beyond the horizon, and new regions of space are constantly coming into view. This means that the observable universe is not a static, unchanging realm, but a dynamic and ever-shifting domain. With each passing moment, the universe gets a little larger in terms of what we can observe, though vast regions remain forever out of our grasp.
If there is so much of the universe that we will never see or know about, does that mean it has no bearing on our understanding of the cosmos? Some scientists have argued that the unobservable universe is, for all practical purposes, irrelevant to our current understanding. What exists beyond the cosmic horizon may have no effect on the structure or fate of the observable universe. However, this view is not universally accepted. Many cosmologists believe that even though we cannot observe distant regions directly, the physics governing the universe, such as the laws of gravity, relativity, and quantum mechanics, applies uniformly, no matter how far away an object is. This suggests that the unobservable universe may still follow the same rules, and understanding its properties could help complete our picture of the cosmos.
The cosmic horizon also implies that the universe itself is much larger than what we can directly observe. What lies beyond that horizon? Could there be more galaxies, more stars, and perhaps even other regions of the universe that are radically different from what we see? Some theories suggest that the universe may be infinite, extending far beyond the limits of our observable bubble, with galaxies, stars, and even cosmic structures continuing forever. In this view, the universe would never end, and our observable universe would be just a minuscule fraction of a much larger, infinite expanse. In contrast, other theories suggest that the universe may be finite, but still incredibly vast. According to this idea, space might curve back on itself, creating a closed loop. In this scenario, what lies beyond the observable universe would be a continuation of the same structure we see in our own cosmic neighborhood, but we may never be able to access it because of the limits imposed by the cosmic horizon. Perhaps our universe is just one of many in a multiverse. If this is the case, the unobservable universe could be just one part of a vast, possibly infinite set of parallel universes, each separated by its own cosmic horizon. The notion of the unobservable universe also brings us to a paradox. If we can never observe what lies beyond the cosmic horizon, how can we ever know anything about it? The universe, in this sense, could be forever beyond our knowledge. For some, this limitation might feel frustrating, as it represents a boundary that no scientific advancement can cross. No matter how much we learn, there will always be more that we cannot see, no matter how hard we try. However, this doesn't mean that the concept of the unobservable universe is without value. On the contrary, it presents us with an incredible opportunity to stretch the limits of our imagination and theoretical understanding. While we may never be able to directly observe the distant regions of space, scientists continue to look for indirect ways to learn about them. For example, by studying the CMB, scientists can learn about the early stages of the universe, even beyond the current observable limits. They can also look for patterns in the distribution of galaxies that might provide clues about the universe's structure beyond the horizon. As our technologies advance and our theories evolve, we may find new ways to probe the limits of the observable universe, and perhaps one day catch a glimpse of the cosmic landscape that lies just beyond the edge of our sight. Entropy story. In a vast universe, in the cosmic dance of stars, galaxies, and black holes, there is an invisible force quietly dictating the future of everything: entropy. At its core, entropy is a measure of disorder or randomness. In the most familiar setting, we experience entropy every day when a tidy room gradually becomes messier with time, even without any intervention. The second law of thermodynamics states that in a closed system, entropy will always increase over time, meaning that systems will naturally evolve toward a state of greater disorder. This law is just as true for the universe as it is for any other system.
Over cosmic timescales, stars burn their fuel and reach the end of their life cycles. Galaxies collide and merge, and matter spreads out, increasing the overall entropy of the universe. Entropy provides a thermodynamic arrow of time, a direction that time seems to move. It's a universal trend that everything, from the smallest particles to the largest galaxies, tends toward a state of higher entropy. This means that in the early universe, When the cosmos was dense, hot, and relatively simple, entropy was lower. As the universe expanded and cooled, complexity and order were created. Stars formed, galaxies clustered together, and life emerged on Earth. But as time progresses, entropy increases, and all these structures will eventually break down and return to a state of greater disorder.
When we think about entropy in the context of the universe, the term heat death often comes up. This concept describes a potential end state of the universe, where entropy has reached its maximum possible value. In this scenario, all stars would burn out, galaxies would spread apart, and the universe would become a cold, dark, and empty place. The stars that light up the night sky today would be distant memories, their once vibrant energy now dispersed across an ever-expanding cosmos. There would be no life, no movement, and no interactions. Everything would be in a state of maximum disorder, where no further useful energy could be extracted from the system. This idea of the heat death of the universe sounds bleak, but it is one of the most significant predictions that comes from the thermodynamic perspective of entropy. The universe, as it continues to expand, will eventually run out of usable energy. In a universe governed by entropy, it seems that all paths lead toward an end of stasis and stillness, where nothing changes anymore.
Yet,
There are nuances to this thermodynamic fate. While entropy might dictate the eventual disintegration of cosmic structures, the journey towards that ultimate state is not a straight path. The universe is constantly evolving, and different processes contribute to the ever-changing levels of entropy. Some areas of the cosmos experience a local increase in order as stars form and galaxies collide, while other areas see more disorder as black holes devour matter and scatter it across space. In fact, the very existence of stars and galaxies is a result of local decreases in entropy. When matter comes together under the force of gravity to form a star, it reaches a higher state of order, creating a dense, hot core capable of nuclear fusion. This process is what fuels stars and gives them energy. The formation of stars is a temporary local reduction in entropy. However, this order is never permanent. The star will eventually exhaust its fuel, expanding into a red giant, shedding its outer layers, and leaving behind a dense core in the form of a white dwarf, neutron star, or black hole. The energy produced during a star's life cycle is released into space, increasing the overall entropy of the universe.
while they represent one of the most extreme forms of gravitational collapse, black holes also offer a paradox in the study of entropy. According to the laws of thermodynamics, black holes have entropy themselves, which is proportional to their surface area rather than their volume. This was a revolutionary insight brought about by physicists like Stephen Hawking, who discovered that black holes can radiate energy, a phenomenon known as Hawking radiation. In this way, black holes seem to challenge traditional understandings of entropy, and they have become a central area of research in modern cosmology, particularly when trying to understand the intersection of thermodynamics, quantum mechanics, and gravity.
As the universe expands and stars burn out, the amount of usable energy decreases, and the universe will gradually approach a state where no significant processes occur anymore. This heat death scenario may take trillions of years to unfold, but it is the natural consequence of a universe governed by thermodynamic principles.
There are some theorists who speculate that in the far future, the universe might experience a big rip instead of a heat death, where the universe continues expanding at an accelerating rate until the very fabric of space itself is torn apart. While this theory is still debated, it presents a different vision of the end of the universe.
Understanding entropy is key to understanding not only how the universe came to be, but also where it is heading. Even the most beautiful structures in the universe, like nebulae and star clusters, are merely temporary patterns that will eventually fade into cosmic oblivion. In this sense,
Entropy is a reminder that the universe is constantly in motion, constantly changing. In the grand scheme, this increase in entropy is what has allowed the universe to evolve in the way it has. It is the very reason that stars have the chance to shine and that life emerged on Earth. Entropy is both a creator and a destroyer.
To slow down, halt, and reverse. This would initiate a contraction phase, where galaxies, stars, and other structures are drawn back together. The idea is that the more matter the universe contains, the more likely it is that the universe will eventually collapse back into itself, setting the stage for a new Big Bang and the next expansion phase.
However, modern cosmology presents an interesting twist on this idea, especially with the discovery of dark energy, which complicates the Big Bounce theory. If dark energy continues to dominate, it could prevent the universe from contracting at all, leading to the more widely accepted Big Freeze scenario, in which the universe expands forever.
However, some variants of the Big Bounce theory propose that the role of dark energy could change over time. In this model, dark energy could eventually weaken or even reverse its influence, allowing gravity to regain control and trigger a contraction. This transition, if it occurs, would then lead to the Big Crunch and ultimately to the next bounce.
Quantum effects may play a major role in the behavior of space-time at extremely small scales, such as near the singularity of a collapsed universe. Quantum fluctuations could allow for the smooth transition from contraction to expansion, preventing the kind of catastrophic collapse that might occur in other scenarios. This quantum nature of the universe could make the Big Bounce more likely, as it suggests that the laws of physics could support the transition from one cycle to the next, without the universe getting trapped in a dead-end singularity. One of the most significant obstacles is the lack of direct evidence for a previous bounce. Current cosmological data, including the CMB, suggests that the universe began in a singularity we call the Big Bang. But there is no clear evidence that the universe underwent any earlier cycles of expansion and contraction. In fact, the idea of a cyclical universe is in direct contrast to the more widely accepted notion of a single beginning, with the Big Bang marking the origin of everything. To further complicate matters, there is the question of how entropy fits into the Big Bounce theory. In the current universe, entropy has been steadily increasing, and according to the second law of thermodynamics, the overall disorder in the universe must continue to rise over time. If the universe undergoes repeated cycles of contraction and expansion, the question arises as to how entropy could reset after each bounce.
Some proponents of the Big Bounce theory suggest that entropy could be partially reset with each cycle, while others propose more complex mechanisms that allow the universe to continue cycling without accumulating too much disorder. How this would work remains a mystery, as the mechanisms behind entropy in a cyclic universe are not fully understood.
The Big Bounce theory often runs into difficulties when trying to explain the detailed structure of the universe, such as the formation of galaxies, stars, and other cosmic structures. In a universe that goes through repeated expansions and contractions, the conditions for star formation and galaxy evolution may not follow the patterns we see today. The question of how the universe could maintain its structure through an infinite series of bounces remains a topic of debate and research.
Some models suggest that each bounce might create a slightly different universe, with new structures forming each time, while others propose that the universe's structure is preserved in some way through each cycle. Whether or not the Big Bounce will prove to be the ultimate fate of the universe is still an open question, but its cyclical vision of cosmic destiny provides an intriguing alternative to more traditional views of the universe's ending. Cyclic models of the universe, new insights in old ideas. The concept of a cyclic universe is one of the oldest ideas in cosmology. For thousands of years, philosophers and scientists have wondered if the universe's existence is defined by a single birth and death, or whether it undergoes repeated cycles of creation and destruction.
While the idea of a cyclic cosmos has ancient roots in philosophies and early scientific models, modern cosmology has breathed new life into these old ideas, using new data and theoretical frameworks to explore how the universe might function as a series of recurring cycles rather than a one-time event.
In Hindu cosmology, the universe is thought to undergo an endless cycle of creation, preservation, and destruction, a concept that inspired similar ideas in Western thought. In ancient Greek philosophy, thinkers like Plato and Aristotle pondered whether the universe had always existed in a constant, unchanging state, or if it had experienced cycles of rebirth.
However, it was not until the 20th century, with the advent of modern physics and the understanding of cosmological principles, that the cyclic universe model began to gain more scientific attention.
Modern cyclic models, while building on older ideas, take into account the growing body of cosmological data, particularly from the discovery of dark energy, which is driving the accelerated expansion of the universe.
One prominent theory is the ekpyrotic model, or cyclic model of the universe, proposed by physicists Paul Steinhardt and Neil Turok. This model, introduced in the early 2000s, suggests that the universe's cycles could be the result of collisions between higher dimensional branes, or multidimensional objects, in string theory.
According to this idea, our universe exists on one of these branes, and the cycle of cosmic expansion and contraction is driven by the interactions of these branes. In this model, the universe does not start from a singularity in the traditional sense, but instead undergoes periodic bounces driven by these collisions.
Rather than a universe collapsing and then exploding again in a new Big Bang, the ekpyrotic model suggests that each cycle is triggered by the collision of branes, which causes a dramatic release of energy that initiates a new cycle of expansion.
This model has received attention due to its ability to address some of the challenges posed by traditional cyclic models, including the problem of entropy accumulation in each cycle, which would otherwise make the universe progressively more disordered with each iteration.
Another fascinating idea is the conformal cyclic cosmology, or CCC, proposed by physicist Roger Penrose. The CCC model builds on the idea of a cyclic universe, but suggests that each cycle is not separated by a dramatic big crunch, but instead fades into an infinite future. According to Penrose, as the universe expands, matter and energy become more spread out and eventually reach a state of perfect smoothness, where the distinction between the past and future disappears. In this scenario, the current universe's far future, dominated by dark energy and a smooth, uniform universe, would seamlessly transition into the beginning of the next cycle, starting with a new Big Bang-like event.
Penrose's model proposes that each cycle could last for a vastly long period, and each successive cycle is effectively a new beginning for the universe, with the conditions of the previous cycle leaving a kind of memory imprint.
While CCC is an elegant theoretical model, it too faces challenges, most notably the need for further evidence to support the idea that entropy in the universe could be reset as the universe transitions between cycles. Nonetheless, it provides a fascinating framework for thinking about the universe's long-term evolution, suggesting that the universe's history may be composed of many epochs, each one more mysterious than the last.
As modern cosmology continues to gather data through powerful telescopes and experiments, it may yet uncover more evidence supporting the idea that the universe is not a one-time creation, but a continuous process of birth, death, and rebirth. Whether or not cyclic models become a central feature of cosmological theory remains to be seen.
but they certainly offer an exciting alternative to the more conventional theories about the universe's past and future.
Higher dimensions and brain cosmology, multiverse perspectives.
At first glance, the thought of higher dimensions beyond our familiar three-dimensional space can seem almost impossible to grasp. After all, we live in a world where objects and events are typically confined to the three dimensions we interact with daily: length, width, and height.
But in the early 20th century, Albert Einstein's relativity introduced a radically new way of looking at the universe, revealing that time and space are interconnected, forming a four-dimensional fabric known as space-time.
Since then, the idea of extra dimensions has been pursued by physicists, with increasingly sophisticated theories suggesting that more dimensions could exist beyond the four we observe.
The theory of higher dimensions gains significant attention, with string theory, a framework that attempts to reconcile quantum mechanics and general relativity. According to string theory, the fundamental particles that make up matter are not point-like, as previously believed, but are instead tiny vibrating strings. These strings vibrate in multiple dimensions, potentially beyond the familiar four.
In the simplest versions of string theory, there are 10 dimensions, 9 of space and 1 of time. Though some variations propose as many as 11 or 12 dimensions. But if these extra dimensions exist, why can't we perceive them?
The answer, according to string theory and related models, lies in the way the extra dimensions are structured. Instead of extending through all of space, these additional dimensions may be curled up or compactified in such a way that they are too small to be noticed at the scale of human observation.
Imagine a garden hose. From a distance, it appears to be a one-dimensional line, but if you look closely, you see it has a circular cross-section. This would be analogous to the extra dimensions being curled up into tiny hidden spaces. These extra dimensions may not be physically noticeable in everyday life, but they could play a crucial role in the fundamental workings of the universe.